Thank you very much, and welcome everyone. My name is Zsolt, and in this presentation, I will tell you about the important role that surface fossil magnetic fields play in massive star evolution. So magnetic fields spread through molecular clouds, and therefore stars form in a magnetized medium. At the other end of the spectrum, stellar end products also seem to be magnetized with a 100% incidence rate. The question, therefore, is what happens to the magnetic flux between these two phases during massive star evolution? In fact, Spitzer's conclusion was that given the available magnetic flux at star formation, stars should generally be magnetized. However, large-scale spectropolarimetric surveys have shown that in most cases, strong surface magnetic fields are not detected in massive stars. This could perhaps be explained by expelling and destroying the magnetic flux, or having a remnant field underneath the surface of the star. Nonetheless, strong magnetic fields are already detected at least in intermediate mass pre-main sequence stars, suggesting that the acquisition of the magnetic field indeed takes place in the early phases. Also, the incidence of magnetism is roughly constant for all stars that possess radiative envelopes. Magnetic fields are detected in AP, BP, OF?P, as well as seemingly chemically normal stars. Finally, the detections remain limited to the galaxy, but we have no reason to think that stellar magnetism would be absent in the LMC, SMC, and beyond. It is very important, though, that we distinguish between two kinds of magnetic fields. Fossil fields are such that they evolve only by slow ohmic dissipation. They were once generated, and then the generating mechanism was switched off, leaving behind an organized, large-scale equilibrium magnetic field. Dynamo fields, on the other hand, require a continuous induction to sustain the magnetic field. Dynamo fields are small-scale, they vary on a short alpha time scale, and they strongly correlate with stellar parameters, none of which is observed in massive stars. Therefore, our current understanding is that the observed strong surface magnetic fields of massive stars are of fossil origin and cannot be explained by dynamo mechanisms. The fossil magnetic field leads to two interactions with stellar winds and stellar rotation. First, the magnetic field lines channel and trap wind material, thereby reducing the effective mass loss rate of the star. Second, the magnetic field lines very efficiently transport angular momentum completely independent of the plasma. As the star rotates, the magnetic field lines are sheared, since rotation forces the magnetic field to bend and twist in the azimuthal direction. Then the magnetic field can impart angular momentum to the surrounding wind material, which will carry it away from the system. However, the exact details of the spin down depend on the configuration of the magnetic field. If it is a dipole, we could expect that all layers of the star will spin down. This is not so trivial for more complex magnetic field geometries, which are now identified in a number of cases. Here, the ZDI map and MHD simulation show that the strong magnetic flux may only affect some parts of the envelope, but perhaps not the stellar core. Thus, we should expect that magnetic braking only concerns the surface layers of the star. Finally, let me mention that both mechanisms, mass loss quenching and magnetic braking, are directly evidenced by observations. Okay, so to evaluate the quantitative impact of magnetic mass loss quenching, I show here the mass evolution of 4 models, each with 60 solar masses initially. The color coding shows the escaping wind fraction. The non-magnetic model loses about 14 solar masses on the main sequence, whereas strong magnetic fields imply that essentially all of the initial mass could be retained. On the plot to the left, the reduction in mass loss rates by 2 different mechanisms are compared. The horizontal axis shows the Alfvén radius. The larger the Alfvén radius, the stronger the magnetic field, and the more mass the magnetosphere can confine and channel back onto the surface of the star. The vertical axis shows how m dot depends on metallicity. we see that magnetic fields already at galactic metallicity can lead to a very significant reduction in the mass loss rates, thereby allowing for producing heavy stellar mass black holes and possible gravitational wave progenitors. You may also hear more about magnetic mass loss quenching from Sébastien Martinet. Let me also emphasize that magnetic mass loss quenching depends on the uncertainties in mass loss rates. Namely, you see here the modeled evolution of mass loss rates in two tracks from commonly used grids. The first thing to note is that the predicted bistability jump and its implementation lead to a very large increase in the modeled mass loss rates, which is not supported by empirically determined rates of blue supergiants. The direct consequence of this may affect complete evolutionary pathways to red supergiants and Wolf-Rayet stars. Also, the increased mass loss rates imply low rotational velocities, which would not be compatible with recent V-Sine measurements of B-type stars. Therefore, with my current undergraduate student Freek, we're looking into the quantitative consequences of using various mass loss prescriptions. One significant impact indeed concerns the measurable rotational velocities. Also, an interesting question is whether luminous blue variables would have such a large jump. On this plot, I show empirically inferred mass loss rates of the prototypical LBV star AG car. Despite that the inferred mass loss rates indeed span a large range, the data does not seem to suggest a jump, perhaps a slow monotonic increase. So about magnetic braking. On this plot, I showed the normalized rotational evolution of the models. The non-magnetic model with purple dashed line spins down due to mass loss and is the slowest to spin down. Models with magnetic braking show that, as expected, the stronger the magnetic field, the more rapidly the surface rotation breaks. The dotted line represents the case when the entire star spins down, and the solid line shows when the surface is undergoing strong braking. It is, of course, always a lot easier and faster to spin down the surface only. So let's see this in practice. The observations here are shown with marker sizes corresponding to the measured fossil field strength, and models with 20, 50, and 80% of critical rotation at the ZAMS are also shown. The generally good agreement verifies and validates the modeling approach. As we see, the currently slowly rotating evolved stars lead to a degenerate solution, as they could originate from fast or slow rotators at the ZAMS. With these understandings, we can immediately draw two conclusions from the HRD. First, magnetic stars, regardless of their initial rotation rate, spin down and converge towards a slow rotating solution. But despite the almost overlapping tracks, the surface abundances and, importantly, the stellar ages are not identical. Second, I also demonstrate here that fast rotating models are substantially different and that can largely impact the derived stellar parameters. Overall, we see that observed magnetic stars need to be compared with evolutionary tracks and isochrones where the impact of the surface fossil field is accounted for. The Hunter diagram here shows surface nitrogen enrichment against the projected rotational velocity.
2 minutes left.
Thank you. The model evolution begins at the lower right corner. As we see, magnetic stars rapidly spin down. Nevertheless, these models produce a significant enrichment, making them compatible with group 2 stars, which cannot be explained with standard evolutionary models. Of course, the enrichment depends on which mixing prescription and efficiencies are used. So let's see this applied to Tau SCO, a magnetic B-type star. The Kiel diagram on the left shows that the apparent age of the star must be less than 6 million years, as indicated by the color coding. However, the Hunter diagram, now plotted against rotation period, which is very, very accurately known, is not compatible with that age. In the single star scenario, one could reconcile this discrepancy by assuming a more efficient chemical mixing and a more efficient magnetic braking, essentially speeding up the evolution of the Hunter diagram. However, these departures are not quite warranted, or at least they need to be studied in other stars. This leads to the conclusion that the single star scenario, at least for this star, may be less versatile. Binary evolution, in particular, a stellar merger, may provide an explanation to resolve these issues. So very briefly about the triple M. I show here a simple analytical estimate for the tidal and magnetic braking timescales. Whichever timescale is shorter is expected to drive the rotational evolution. The model is adopted to represent the star shortly after the ZAMS. What this estimate suggests is that in such a closed binary system, the magnetic spin down may be the dominant effect to drive the early rotational evolution. Repeating this experiment with various parameters for the mass ratio, spin rate, and so on suggests that this is generally the case for orbital periods up to about 10 days. In fact, with my undergraduate students, we looked at specific systems. Dani found that in a closed binary with one star hosting a strong magnetic field and the other one not, the stellar ages are still approximately the same, which disfavors a late merger scenario to explain the origin of the magnetic field. Tom studied the inner binary of a triple or perhaps quadruple system, where again one star is strongly magnetic, but the close companion is apparently not. He concluded that their proximity will result in Rostov overflow already on the main sequence. Finally, we are computing a large grid, which can be used for comparisons with observations. These are the first results for a galactic metallicity, the left showing non-magnetic models and the right showing magnetic models. This will shortly be extended to the LMC and SMC. So to summarize, we are studying the impacts of fossil magnetic fields, which have far-reaching consequences. Also, to reiterate, observed magnetic stars need to be compared with appropriate evolutionary models. Thank you.